Hi everyone, welcome to our last lesson for Calc BC on absolute versus conditional convergence. Okay, so many convergent series have negative terms or an alternating pattern, right? We've seen alternating series tests or alternating series, and we used AST, right? Taking the absolute value of each term of a convergent series with some negative terms makes a new positive series that's less likely to converge, right? Because the sum will be greater without the negative terms kind of weighing it down. If the new positive series still is convergent, the original series is actually called absolutely convergent. If the new positive series diverges, the original series with negative terms is called conditionally convergent. If a series converges after taking the absolute value of its terms, it is guaranteed to also converge with no absolute value, right? Which makes sense. It doesn't have those negative terms, making it smaller. Kind of, you can think of direct comparison test, right? When you have a series that is smaller than something, or sorry, smaller than something that converges, then it's also going to converge. Okay, so let's look at number one. If we have the sum from n equals 1 to infinity of -1 to the nth power over n, this is actually the alternating harmonic series. And the alternating harmonic series converges. Now, if I were to take the absolute value of each of the terms, I would get the sum from n equals 1 to infinity of 1 over n, right? Because it's no longer alternating. This is actually just the harmonic series, which we know diverges. Okay, so for this one, we could say that the sum from n equals 1 to infinity of -1 to the n over n is actually just conditionally convergent. It's conditional on the fact that those terms alternate in sign. Okay, so now's a good time. Go ahead and pause here, do numbers 2 and 3. What you want to do is first show that the original series converges, right? And then you take the absolute value of those terms, and then you can see if it's conditionally or absolutely convergent. Okay, so you can unpause, I'll go through them. So let's start with number 2. So we have the sum from n equals 1 to infinity of cosine of n over n squared. And so you could actually rewrite this as the sum from n equals 1 to infinity of cosine of n times 1 over n squared. Now let's think about this. The cosine function oscillates from 1 to -1, so there are some negative terms thrown in there. Times 1 over n squared is a p series that converges. And so you can actually use the direct comparison test here. And so you can compare it the sum from n equals 1 to infinity of 1 over n squared, p equals 2, right, which is greater than 1. This converges by the p-series test. And remember, cosine of n times 1 over n squared, that's going to be less than something that converges. So because the sum from n equals 1, or actually, we don't even need that part. All we need to prove this would be to say that 0 is less than cosine of n times 1 over n squared, which is less than or equal to 1 over n squared, right? For all n from 1 to infinity. And then we can say that this original series converges sorry about that. No, Scar, stop. No, no barking. Okay. She's been so good the whole time I've been filming videos, and my dog had to walk by. Okay. Converges by direct comparison test. Okay. Got a nice little appearance from Scar. Okay, so we're gonna divide that off. What we want to do is now compare it to the absolute value. And notice now those terms are no longer going to be, sorry, she's back. Okay. No. Now those terms are no longer going to be alternating, right? Cosine is not going to be alternating between 1 and -1 anymore. So we want to take the sum from n equals 1 to infinity of the absolute value of cosine of n over n squared. You don't have to worry about the n squared. It's not going to ever be negative. So think about the absolute value of cosine of n over n squared. Okay, now we could actually use the same direct comparison test. So we can compare to the sum from n equals 1 to infinity of 1 over n squared. We already showed that this converges by PST. Okay. Now, the absolute value of cosine of n over n squared, it's actually still less than or equal to 1 over n squared, right? Because what ends up happening is you may have certain terms, right, that even though it's not alternating, you have a smaller numerator at times, right? And so when you divide that by a bigger number, it's going to be smaller. So it'll be less than or equal to, because the absolute value of cosine of n is oscillating now between 0 and 1. And so that still holds true. So this still satisfies direct comparison test. So therefore, the sum from n equals 1 to infinity of the absolute value of cosine of n over n squared converges by direct comparison test. And so therefore, the sum from n equals 1 to infinity of cosine of n over n squared is absolutely convergent. So this one was a little bit trickier. You had to do a little more thinking about what test to use because of that cosine of n. Direct comparison test is always a good one to choose when you have a multiplication of two different functions going on, where it's not quite as easy, especially when you can't do ratio test. I would not want to do ratio test with a cosine or any kind of trig function. Okay, last one, we have the sum from n equals 1 to infinity of negative e to the n over n to the e. Okay, this one I would definitely choose ratio test to show the original convergence or divergence. So let's start there. The limit as n approaches infinity of the absolute value of negative e to the n plus 1 over n plus 1 to the e times the reciprocal of the original n to the e over negative e to the n. Okay, let's keep going. We have the limit as n approaches infinity times we have negative e to the nth power times negative e over n plus 1 to the e times n to the e over negative e to the n. All right, these guys cancel. We end up with the limit as n approaches infinity of the absolute value of negative e times n to the e over n plus 1 to the e. Okay, well, this equals the absolute value of negative e because the degree of the numerator and denominator are equivalent, even though it's a weird degree of e, right? Which equals e. Well, there's a problem here. E is not less than 1, right? It's 2.718 approximately. Because E is greater than 1, actually, this original series, the sum from n equals 1 to infinity of negative e to the n over n to the e actually diverges by the ratio test. So this one doesn't converge at all. It just diverges, and that's it. And so that is all for that one. All right, so that is all for today. And actually, that is all for sequences and series in general. So thank you. And this ends here. Good luck studying for the AP exam.